heat flux, convective heat flux, with a heat transfer coefficient that's specified by our parameter H0. And then we're going to apply it to to all boundaries. Now this is because we assume we know the thermal environment that's enclosing this microresistor beam. For example, it's in contact with air, and this natural convection can be approximated by a constant heat transfer coefficient. Now, in addition to a heat flux, because this beam is likely fixed to a large circuit board, which probably has a large thermal mass, so we can constrain the temperature of this beam at these 2 feet. So we can do that by add a temperature boundary condition, and then select these 2 surfaces. So that's all we have to do in terms of the heat transfer in solids. Let me collapse this node, and then we move on to solid mechanics. Now in this case, all we have to do again is to fix these 2 feet of the beam. So we can do that by right-click solid mechanics, add a fixed constraint, and select these 2 surfaces. And you'll see that this basically prescribes a 0 displacement field to the dependent variable u that we're solving here. And that's all we have to do in terms of solid mechanics. And again, let's work from top to the bottom down this model builder tree. We'll see 2 multiphysics nodes. The thermal expansion will couple heat transfer with solid mechanics, and the electromagnetic heating will couple the electron currents with heat transfer in solids. So these are automatically set up for us, so there's nothing that we need to do here. So let me just collapse these nodes, and then we'll have to generate a mesh. Now in this case, Comsol has its built-in algorithms for mesh generation, and the default mesh uses a free tetrahedral mesh, which is usually very good, and there's nothing that you need to do other than just click this build off button, and you'll see our 3-dimensional domain is instantly matched to these 3 tetrahedral elements. And that's all we have to do in terms of the mesh. And then we can basically just go to study and click compute. And then Comsol will do the heavy lifting in the background, solve these equations for us. See, it takes like 5 seconds to solve these 3 physics interfaces. And we see that there are a few post-processing plots that are generated automatically for us because we have selected these physics interfaces. Now, for example, we can see the electric potential, the temperature distribution in the entire domain. You can look at the isothermal contours, or the stress and the deformation solved by the solid mechanics interface. Now, remember our objective today. We want to know what's the current that flows through the beam as a result of the applied voltage. Now, we can do that by go to derived values, and let's add a surface integration here. And let's select one of the feet here. And under the expressions, we can go to the built-in variables, electric currents, currents and charge, and add a normal current density. So if we integrate the normal current density over this boundary, that will give us the electric current that flows through the beam. So if I click evaluate, you'll see that number shows up here in table 1. So here we see that the value is 0.005 amp. So now we have an answer with regard to the magnitude of the electric currents that flows through the beam. Remember, we might also have other questions like, okay, so will the Joule heating cause a meltdown? Will this beam overheat? So we can do that by, again, using derived values and add a volume maximum here. Select the domain, and the expression here is T. So this gives us a maximum temperature in the entire domain. And if we click evaluate, we'll see that value is around 400 K. So that's well below the melting point of titanium. So we know that the 0.1 volt that we applied is safe. All right, so lastly, let's see how we can generate a plot like the one that's shown in the slides. A plot that can show all of those solutions together, like a multi-physics plot. So what I did here was just right-click results, add a 3D plot group, and let's call this multi-physics. And so let's see how we can have a really nice plot built from scratch. Now let's first add a surface plot here, and let's change the expression to temperature and click plot. You'll see the temperature field is plotted on the surface of the domain. Just for consistency, let's change this color table to thermal light. And we'll see a highest temperature here at the middle of the beam. Now, in addition to the temperature, there are a lot of things that we can do. For example, we can add a deformation to this plot. So what I did here was right-click surface and add a deformation node. And you'll see it automatically uses the displacement field components, UVW, and couple it to the plot. So we can visualize the deformation together with the temperature. Now, in addition, so now we have two physics already here shown in this plot. The one last thing we need is to show the electric current that flows through the beam. Now, to show the inside of this beam, what we can do here is to add a selection. We can first select all boundaries and deselect some of these boundaries on this side. And then let's click plot. You'll see that these boundaries are now hidden because they're excluded from our selection, but we can still see the temperature distribution and the deformation of the beam. Now, what we can do here is add a streamline plot, and you'll see that as a default, it'll use the electric current components as the X, Y, Z components. For the positioning, we can use uniform density. Maybe we can make it a little denser than what it is right now. You'll see these red streamlines right now inside the beam. We can also add deformation to it so that it'll be more consistent with the temperature plot. And we can also add some color expressions, for example, the voltage. So we can see that it's 0.1 volts here, and it gradually decreases to 0 when it reaches the other foot. Now, we can also customize the line style here. We can change it to Q. Let's give it a radius. Let's see what would be a good value. 0.3 micron, scale factor of 1. And we can even add an arrows to these streamlines. So that way it's clearer with a larger radius. So yeah, that's the entire workflow. That's how we solve this multi-physics problem, and we can look at the electric current, the temperature, and these kind of multi-physics plot. All right, before I go back to the presentation, are there any other questions? All right, I see a couple more questions here. Can the post-processing step be done into the Comsol GUI? Well, yes, we just demonstrated how to do that, like these plots. Next question. I'm looking forward to simulate ventilation in buildings. How should be the workflow when I have a model from Revit, for example? Well, if you have the live link for Revit or the CAD import module, you can certainly just import that geometry into Comsol using basically the same thing that we did there, just right-click geometry and import. Next question. Where was the geometry file made? In AutoCAD? Oh, in this case, it's a native Comsol CAD. So we made it in Comsol and we just exported it. Since it's a relatively simple geometry, and of course Comsol can handle that. Let's see any other questions. Can we export the properties table in Excel or similar format? Yes, we can certainly do that. So, for example, the easiest way would be just to go to these tables and then, So let me first talk about the post-processing results. If you want to export these, simplest way is to copy and paste these values. You'll see these can be selected. You can just simply copy and paste to an Excel spreadsheet. Now, in terms of material properties, these values can also be copied and pasted to an Excel spreadsheet if you would like to do that. All right, let's go back to the slides here. In a little trouble. Okay, here it is. All right, so we've just demonstrated how to solve a multiphysics model in the model builder. Now, in addition to that, another major innovation of Comsol is what we call the application builder. Now, as you can see on this page, this application builder has a much more simplified user interface. So the user of an app can simply specify some input parameters and then just click compute and get results right away without having to know how to set up the model. So then, an experienced people in simulation can then build this model and convert it to an app to share it with people who might be new to simulation. Now let's see how this works, and we'll demonstrate how to build an app using the model that we just solved. So if you have Comsol on Windows, you'll see here under the Home tab, there's an Application Builder button. So right now, this functionality is only available on Windows. If you click the Application Builder, that'll take us from the Model Builder to the Application Builder. Now, the simplest way to build a new app is to use this new form. It's similar to the Model Wizard. Basically, it kickstart this process for building an app. Now, first, it asks us for some inputs and outputs. We'll definitely need these two inputs, like the voltage and the heat transfer coefficient. And for outputs, we're interested in the total current and also the maximum temperature. So I can just select them and add them to my app. And you'll see these here under the preview. Let's go to graphics. What we can do here is to add some plots, like the multiphysics plot that we just worked on. So I'll include that here. And also, let's add another default plot, maybe the isothermal contour. So you see that these two graphics windows are added there. And then let's go to buttons. So we'll definitely need a compute button, as you can see here. Maybe we want to see the mesh, so we can add a plot mesh. Let's add another one that plots the electric potential or plot the multiphysics. So then you'll see these buttons in the graphics windows parameters are all here. Let's click OK. And then we can see this form or the graphical user interface of this app right here on the screen. Now, the idea here is you can rearrange these however you want. You can basically it's like a PowerPoint slide, so you can rearrange these to whatever size you want. Maybe you can drag the compute button to here, the plot mesh button. Let's line them here all on the top. So we have two plots, two plotting buttons, and that's a very simple demonstration of an app. Now let's see how we can test this. So you just go to this ribbon here and click Test Application, and then it'll launch this app that we just built right here. And you'll see here we can change some inputs, and the current and temperature will be displayed here, and we'll see these plots. For example, if we click Plot Mesh, then this multiphysics plot will become the mesh plot. We can plot this multiphysics plot or the electric potential plot. Now, if you give this app to another person who might be new to simulation, they can just simply change the parameters. For example, let's change the voltage that we apply across the beam to 0.2 volts, and then we can